Hello everyone. We are into our first set of video notes. So terribly exciting. Welcome. By now you have, that's a very large hint as in it should have been done by now, completed the investigation. And so you saw that, and many of you may have known that piecewise functions are pieces of various functions restricted by their domains and put together to create a new function. Okay, you've seen them. They tend to trip us up sometimes. So we're going to walk through how to do and create and graph and analyze and answer questions on these piecewise functions. Okay, so here we go. So for example, number 1, it wants us to graph each of the functions below. So that's what we're going to do first. So for number 1, y equals 2x plus 1. It's in slope-intercept form. So my y-intercept is at 1. And I'm going to go up 2 units and over 1, up 2 units and over 1. You're more than welcome to go down 2 units and 1 to the left if you would like. And oh my, we're going to redo that. I am on a computer, and so my lines tend to be a little not as nice as I would like. Okay, for number 2, it wants us to do the same. Okay, so we see that we have a y-intercept at 7 halves, 3 halves, 3.5. 1, 2, 3.5. And then our slope is -1/2. So I'm going to go down 1, but I'm going to make sure that I go down to the half. Okay, don't go down to the next integer. Not what we're doing, yeah? Go down to 1 unit and over 2, and then down 1 unit and over 2. I am going to go up 1 and over 2 units to the left, basically working backwards so that I can have a little bit more of my line. Don't forget that the line goes on forever. And how in the world are we showing that? Because let's be real, we don't got time for that. No, realistically, I can't sit here and draw an infinite line. So we use our arrows. Very important. Okay, the last one, the last piece that we're going to look at is y equals 1.5. All right, so that means at the y-axis, I'm going to intersect at 1.5. And regardless of what my x value is, the y value is going to correspond to 1.5. So it is a horizontal line with arrows at the end. Fantastic. Okay, so then it says to please highlight the following portion of the graphs. I'm going to switch to my highlighter. In graph number 1, it wants us to highlight the portion of the graph in the domain where x is less than 1. Okay, so I'm going to switch colors real quick. Be careful. Less than, oh gosh, less than means that I'm going to be an open circle when graphing. So I'm going to make a little notation here so that when I do go back to putting all these pieces together, I remember, it's not a D, that's a C. I remember that it's an open circle. Okay, so for highlighters then, let's go ahead and, oh my. See, this is the fun part for you guys. You're like, oh, Patterson, doing great. Okay. So x is less than 1. So I'm going to identify where 1 is on my x-axis. I'm going to go to my line, and I'm going to highlight the portion where x is less than 1. The domain is less than 1. Okay, remember x values are in the domain. All right, for that middle, for number 2, highlight the portion where x is greater than or equal to 1, okay, but less than 4. So I'm going to be highlighting this piece of the function. And last but not least, for graph 3, where x is greater than or equal to 4, all right, so then that's from here on. Okay, so we graphed the 3 given functions. They are functions because their x values do not repeat. Their domain elements are unique. Okay, they passed the vertical line test, right? And then we went and highlighted where their domains were restricted. So now it's going to ask us to graph the function that's a piecewise function. And it's exactly what we just, what we just highlighted. This is the first one. This is the second one. That's the third one. Okay, that's all a piecewise function is taking these snippets from the various functions, pulling them away from the original and putting them together to make some new, sometimes super cool, sometimes funky and wonky new functions, okay? All right, so for the first one, I'm going to switch colors real quick if I can, real quick. Yeah, that's a laugh. Okay, I'm starting here, and I'll do this one in yellow, okay? So at 1, 3, remember, open circle. At 1, 3, I'm going to have an open circle. I'm going to make this a little bit bigger for me. And the next point that I see is 0, 1. And I also see a point at -1, -1. So that's going to help me draw this part of the piecewise function. Since x is less than 1, it is an open circle and it goes on forever to the left. Okay. All right. For the middle part, let's go ahead and switch colors just so we can see the distinctions. I'll use green. Why not? Maybe. Okay. First point I see is here and the last point is there. Now it has 2 restrictions on the domain, which means it's not going to be an array, it's going to be a segment. The first starts at 1, 1, 3, and it's a closed circle. So at 1, 3, I'm going to fill in the circle that I have there. Okay, and then it looks like I end at 4, 1.5. That is an open circle. Okay, open circle because it doesn't have the equal to. So I'm not equal to that value. I exist less than the value, but I get really infinitesimally, yep, say that 5 times fast. I get really close. So that's why we have the open circle. So I'm going to go over 1, 2, 3, 4, and up to 1.5. And I'm going to connect those 2 endpoints for that part of the piecewise function. All right, to keep things fun, we've got yellow, green, let's go purple. Is that purple? Looks like a dark blue. Let's go purple. All right. And that will be our last part of the function. It starts here and it goes off into infinity to the right-hand side. How do I know? There's only one restriction. Okay, x is greater than or equal to 4. And it just so happens that it is also going to fill in this circle. It is at 4, 1.5. And then I'm going to extend out to the right-hand side. The more points you have on your lines, on your segments, on your functions, the more accurate the shape and the behavior of the function will be represented. For a line, obviously, 2 points make a line. I always suggest 3. Again, the more points you have, the more accurate your function is going to be represented on your graph. All right, let's go back to the color of my pens usually, which is black. So is this a function? Yes. Yes, it is. And how do we know? We know because the x values do not repeat. Now, right here and right here, yes, we have both yellow and green, both green and purple. But remember, the yellow was an open circle. The green filled it in. Therefore, it was only represented at x equals 1 time. For x equals 4, it was only represented 1 time. So therefore, it is a function. The coordinates do not overlap at x equals 1 or x equals 4. Is it continuous? Excellent question. Survey says, yep, it is. And the reason being is because I can draw this function from left to right without picking up my pen or pencil. It is one fluid graph. There aren't any holes, okay? So we say that it is continuous. Now, the domain, remember domain is x values. So I'm going to say that it is the all real numbers because there aren't any breaks. From left to right, every x value is represented. We can't visually see that, but we have our arrows, yeah? And that's what, well, you know, they're there. That's what represents that it's going to go on forever, and that's why they're so important. You can, and I highly recommend getting used to our interval notation. From left to right, our graph goes from -infinity to +infinity. Okay, and you're also welcome to write all real numbers, totally up to you. Range, always go smallest to largest for domain and range. So how far down is my graph going to go? Well, this guy tells me it's going to go all the way down to -infinity. So I'm going to use -infinity. But I stop right here. That's where my graph caps off. It stops at, what is that, 3. And it's a closed, circle. So that means it ends at y equals 3. So I'm going to say that it goes from -infinity to 3, and I'm going to use a bracket because I exist at 3. It is inclusive. Okay, if it was an open circle, I would use a parenthesis because it is non-inclusive. Now, why does infinity have, that's ugly, sorry, have parentheses? Because infinity is never inclusive. It is a concept. We can't ever get to infinity. I know some of you might be really super sad. Buzz Lightyear told me to infinity and beyond. Well, Buzz Lightyear lied. I'm really sorry. But keep in mind, he was a toy and he has dreams just like we all do. If you're shaking your head at me right now, how dare you? Buzz Lightyear has feelings too. But infinity is a concept. Oprah has a ton of money. She's not infinity rich. Okay. So keep that in mind. Now, interval notation is what I have written. If you would like to use set notation, we would say that y is less than or equal to 3. Okay, we include 3 and everything that is smaller than that. Excellent. Ladies and gentlemen, welcome to piecewise functions. Now, there are various ways to graph them. You don't always have to draw all 3 or 2 or 5 functions and then highlight. You're more than welcome to, let's say, for example, this one right here. Yeah, I could make an X and a Y chart. And I know that it's going to be greater than or equal to 4. So I'm going to include 4 and 5, maybe 6. Well, y equals 1.5. So when x is 4, y is 1.5. When x is 5, I'm 1.5 and so forth. And then since it's greater than or equal to, I would just want to maybe write next to this that it's a closed circle so I knew when I was graphing. Okay, let me finish that. There we go. And you could do the same for the others. There's different ways to go about graphing them, either X and Y charts, or feel free to graph them all out and highlight and go from there. Excellent. Okay, skill 1, graphing piecewise functions. I look forward to discussing the investigation and this notes assignment with you. Make sure you guys are attempting the homework.